Now that we've talked about atoms and seen some of the features of the periodic table, one of the really remarkable things about chemistry is that every chemical, every substance that you have ever seen is composed by at most 90 different elements. There's only about 90 elements that are naturally occurring on the surface of the Earth, and some of those are so rare you'll probably never see them. So every color of every fabric, every paint, every metal, every porcelain plate, cells of trees, cells of humans, cells of fungi, plastics, all formed from combinations of only really a handful of elements. What we'd really like to understand in chemistry is how do the atoms combine in such a way to form new substances that have such very different properties than the original elements from which they are formed. Before we get to that point of describing how things stick together, we need to learn some terminology, and that's what we're going to be doing in sections 6 and 7 of chapter 2, talking about what do we mean when we use the words molecules, ions, and compounds. And these have to do with the ways in which these atoms chemically bind together. Let's start by talking about molecules. So a molecule is an electrically neutral collection of two or more tightly bound atoms that behaves like an independent object. Here the emphasis is not on two or more tightly bound atoms, but rather that it behaves like an independent object, so that, for example, one exception to the above rule is that individual atoms of noble gases are also considered molecules, even though they're only single atoms because they don't form chemical combinations with anything, and they act like an independent object floating around. So the idea of a molecule is kind of like the idea of a car. We all know that our automobiles are composed of many, many parts, but those parts are hopefully tightly bound together so that when we drive the car, we think of driving a single thing as opposed to driving a collection of things that is held together. That's kind of the idea of a molecule. Now, in contrast, a compound is a chemical combination of two or more elements. There must be at least two elements to be considered a compound, otherwise it's just an element. So some clarification notes. First of all, not all compounds are composed of molecules. In fact, a very large category of substances are known as ionic compounds, examples of which are calcium oxide and ammonium nitrate. We'll learn how to name those in just a bit. They don't contain any molecules at all, but rather they contain ions that are electrostatically stuck together. That's not the same thing as a molecule. So just because we have a formula does not mean we have a molecule. Secondly, molecules are not necessarily particles of a compound. So several elements exist naturally in molecular form, and among the most common are the diatomic elements. I actually want you to memorize this list of diatomic elements. There's not very many of them. This is it. So anytime I refer to hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, or iodine in terms of macroscopic amounts, say if I say 10 grams of bromine, I am of course talking about the form in which bromine occurs naturally, which is Br2. And I'll tell you right now, diatomic elements are among my favorite elements to include in test questions to see if you remember, without me telling you, that they are diatomic. Now, if we do restrict ourselves to molecular compounds, namely substances that are both molecular and contain two or more elements, there are several ways that we can write these in terms of formulas. We see water, H2O, hydrogen peroxide, H2O2, CH4, CO2. Now, what do these subscripts mean? It turns out it's not quite as simple as you might think. There are at least 3 different types of meanings of subscripts, depending on what sort of formula we're using. So let's look at the different types of formulas. The 3 types of formulas that we will be commonly using in general chemistry are empirical, molecular, and structural. Empirical, the word empirical refers to from experimental data. So this is the simplest formula to calculate based on experimental measurements. In an empirical formula, the subscripts indicate only the simplest ratio of the number of atoms, or if it's an ionic substance, the number of ions present in the compound. Just the simplest ratio. Okay? In a molecular formula, which only applies to molecules, not to ionic compounds, the subscripts indicate the actual number of atoms present of each element in each molecule of the substance. And then finally, in a structural formula, the idea here is it not only shows the actual atoms in the molecule, but shows the order and way in which they are connected to each other. So let's just see a few examples here. Water, of course, the empirical formula is H2O, the molecular formula is H2O. There are literally 2 atoms of hydrogen per molecule of water. The structural formula tells us the order in which those atoms are attached, namely HOH, as opposed to, it could have been HHO, but that's just not how it's attached. This is the correct structural formula. In hydrogen peroxide, this is a molecular substance whose molecular formula, H2O2, tells you that there are 2 hydrogens and 2 oxygens per molecule, but the simplest ratio then in the empirical formula is just 1 H to 1 oxygen. 1 subscripts are always omitted, and as it turns out, this is hooked together in the way HOOH. Ethylene is a molecule with 2 carbons and 4 hydrogens per molecule. Again, the simplest ratio, if you take 4 divided by 2, the simplest ratio is 2 to 1. That would be the empirical formula. And in this case, the structural formula is just a little bit more complicated because it involves a double bond between 2 carbons. And then hydrogens attached there. Sorry, I'm not drawing very well, but there's 2 hydrogens on each carbon and a double bond between them. And then lastly, calcium chloride, because this is an ionic compound, there is no molecular formula. So I would say no molecular formula and no structural formula. It just consists of ions that are electrostatically stuck together, kind of like the way a charged balloon will stick to the wall. So how do we tell whether a substance is a molecular substance or an ionic substance? Well, let's start by being clear about what we mean by an ion. An ion is any atom or tightly bound group of atoms that has a non-zero electric charge. It's either positive or it's negative. And we classify them in 2 categories according to whether they are positive or negative. Positively charged cations like these, ions are called cations, and it is pronounced cation, not cation. Any ion with a positive charge is a cation by definition of cation. So this is sodium ion, calcium ion, iron 3 ion. Anions are ions with negative charges. For example, fluoride, oxide, and nitride ions. And these are all what we would call monatomic ions, meaning simply that they consist of a single atom with a charge on it. Okay? Ordinarily, metals form cations and nonmetals form anions. So if a metal ionizes, it almost always forms a cation and not an anion. And then lastly, we have polyatomic ions. This is the tightly bound group of atoms that has a non-zero charge. So nitrate has a -1 charge. It's not necessarily on an oxygen. It's just collectively the charge on this group of atoms that floats around in solution like a single object. Sulfate ion, arsenate ion, and you can see more of these sorts of polyatomic ions in the ion chart that you'll see in your Canvas files. Now that we know what ions are, we can better understand how to identify whether a compound is an ionic compound or molecular compound. So the way we're going to do this for now in our class, we're going to follow this simple rule. First thing, any compound containing both a metal element and a nonmetal element is ionic. This is another reason why you need to be able to recognize metals and nonmetals by looking at a periodic table. If the compound formula begins with an NH4, an ammonium ion, then it is ionic. And then we'll assume that any other compound, at least for now, we will assume that to be molecular. So fairly simple. Look for a metal and a nonmetal. They're both present, it's ionic. Look for the formula to begin with an NH4. If it does, it's ionic. Otherwise, it's molecular. That's it. So let's just look at some examples and identify these as either ionic or molecular. This formula begins with an NH2. That's not an NH4. So this is molecular. In the next compound, we've got chromium, which is a metal, selenium, which is a nonmetal. Therefore, this is ionic. Here we have silver, metal. Oxygen is a nonmetal. Metal and a nonmetal, it's ionic. Scandium is a metal. Carbon is a nonmetal. Therefore, this is ionic because we have a metal and a nonmetal. Here we start with a hydrogen, which is a nonmetal. Sulfur is a nonmetal. Oxygen is a nonmetal. This is molecular. And lastly, we have a formula that begins with an ammonium. Therefore, this is ionic. Even though there's no metal in it, the ammonium effectively takes the place of a metallic cation. And as I mentioned earlier, ionic compounds really just consist of cations electrostatically stuck to anions with bonds that just are these electrostatic attractions and aren't pointed in any particular directions at all. Ionic formulas are always empirical formulas, meaning that they always show the ratio of the number of ions present in the ionic compound. We always want to pick the smallest number of each ion that could possibly be combined in such a way to create an electrically neutral formula, and always show the cation first. Formulas must not show charges. Even as a side note to yourself, don't put charges on the ions, and you must put parentheses around any polyatomic ions, not monatomic ions, only polyatomic ions that are used more than once. So if there's only one polyatomic ion, you do not show parentheses. So we're just going to work out a few examples here. Down here in our first example, if I have a copper 2+ and an azide with a minus charge, I need 2 minus charges to cancel the 2+. So my formula is going to be, grabbed the wrong color there.